Hi, I'm Dr. Adil Majeed Rather. I'm currently working as a DST Inspired faculty at Department of Chemistry, National Institute of Technology, Srinagar. I would like to thank you, ANRF, for providing this opportunity to present my research work. Our research work is based on designing a functional and adaptive liquid repellent surfaces for water remediation, biomedical, and energy applications. The overall research overview, which includes the fabrication of load sleeve inspired super hydrophobic surfaces, which are water repellent surfaces, as well as the slippery surfaces, which are inspired from Nepenthes pitcher plant. So these surfaces have various applications in designing anti-corrosion and anti-icing surfaces. They are also useful for designing oil water separation materials, as well as their utilization for designing biomedical surfaces for anti-thrombotic applications. So today I will be discussing about these different materials, their design strategies, and their applications in various fields. The concept of wettability starts a long back ago, based on the Young's model. When a liquid droplet is dispensed on a solid smooth surface, it spreads till it achieves an equilibrium contact angle, where and that equilibrium contact angle is measured with Young's equation, where the liquid vapor interface, solid vapor interface, and solid liquid interface meet together at a three-phase contact line, and that contact point we called as and the angle measured at that three-phase contact line is called contact angle. However, when the surface is not extremely smooth, it has some sort of roughness on it, the contact angle on those kind of surface is measured using Wenzel, is explained with the Wenzel method. And that Wenzel method explains when there is a roughness on the surface, the hydrophilic surfaces becomes more hydrophilic, and hydrophobic surfaces become more hydrophobic with increasing the roughness on the surface. And both of these methods we call as homogeneous wetting models, where the liquid has a direct contact with the solid surface. However, these methods are unable to explain a very high contact angle of liquid droplet on the surface. When the liquid droplet has a very high contact angle on the surface, the contact angle on those surface is explained with another model, which is called a Casey-Baxter model. In this model, the contact angle above 150 degree, which we call as super hydrophobic, is explained with this model, and this model which we call as heterogeneous wetting model, because the liquid droplet doesn't have a direct contact with the solid surface because of the presence of trap air in between the rough structure or the micro nano texture. When the contact angle of the liquid droplet on the surface is above 150 degree and the roll-off angle or the sliding angle is less than 10 degree, those surfaces we call as super hydrophobic surfaces. These super hydrophobic surfaces, as I mentioned earlier, are inspired from the load sleeve. If we examine the load sleeve under microscope, under scanning electron microscope, we can see that this load sleeve is not smooth in nature. It has some rough structure on the surface, and that micro texture which is further coated with a waxy nano structures, and the combination of that micro and nano texture in combination with low surface energy which is provided by the waxy coating gives us the super hydrophobic property of lotus leaf. Eventually, this method was replicated in artificial means, and researchers have designed different micro nano textures and to replicate the lotus leaf structure, and it was found the appropriate combination micro and nano texture with an essential low surface energy coating provides the super hydrophobic materials. So in order to achieve the super hydrophobic surfaces in the artificial means, the two criteria need to be fulfilled. One is the dual degree of roughness, which is an appropriate combination of micro and nano texture, as well as the essential low surface energy coating. So the combination of these two criteria gives the super hydrophobic property. In the past, various researchers have designed the super hydrophobic surfaces, but those surfaces were mainly of two-dimensional surfaces, where the super hydrophobic property is limited to the surface only. But when these surfaces were damaged, the inside of the material was not super hydrophobic. So the concept of bulk super hydrophobic material, where the entire surface, both on the surface as well as in the bulk, is super hydrophobic in nature. So if the surface is damaged, the inside surface or the exposed surface is still super hydrophobic. Various three-dimensional super hydrophobic surfaces have been designed previously using different methods like copolymerization and dissolution approach, as well as the layer by layer deposition approach, as well as a candle soot deposition approach. In all these methods, the three-dimensional super hydrophobic materials were designed to create the super hydrophobic property both on the surface as well as in the bulk of the material. However, if we see, these methods are very complex methods, as well as they are tedious or laborious methods to design these three-dimensional super hydrophobic materials. Therefore, our aim was to design the super hydrophobic materials, which are bulk super hydrophobic materials, using a facile and scalable synthetic approach. With that, we have use a very well-known chemical reaction which we call as Michael addition chemical reaction to design the three-dimensional super hydrophobic material. This Michael addition reaction is used for designing various polymers, as well as synthetic polymer bioconjugators, as well as they are used for making dendrimers for DNA delivery, graft polymers, as well as for the synthesis of functional surfaces. So this particular Michael addition we have also used in our studies to design the micro nano texture using Michael addition reaction of cross-linking a polymer with a small cross-linker agent. In our studies, in our research, we have used a branched polyethylene amine and cross-link that amine with a pentaacrylate molecule which acts as a cross-linker, and after mixing them together in an appropriate composition, we designed the micro nano texture, as we can see here. And when we post modify that micro nano texture or this hierarchical texture with an appropriate low surface energy, we created a super hydrophobic surface, and those super hydrophobic surfaces are super hydrophobic both in the bulk as well as on the surface. Further, we have exploited this method for different other designers. As the first method, we have used ethanol as a solvent medium here, and then we found that if we change the reaction solvent, what will happen on the super hydrophobic property as well as the micro nano texture. When we replace the ethanol with the different analogs of ethanol like propanol, butanol, and pentanol, we found that all these different solvents are able to show the super hydrophobic property. And when we increase the hydrocarbon length of the solvent, we can see the micro nanotextures becomes more agglomerated, as we can see in case of pentanol. However, all these surfaces were super hydrophobic in nature. Moreover, this method we can also use to design the super hydrophobic gels without using any solvent, while we can mix this pentaacrylate and polyethylene amine together, and this through this Michael addition reaction mixed together, and we can easily prepare a super hydrophobic gel without using any external solvent, which makes it more environmentally friendly and viable. And this particular method we can also use to design the stretchable super hydrophobic membranes, which could be eventually used for oil water separation. So here we can see that this polyurethane fabric was coated with the super hydrophobic coating, and even after 150% of deformation, the super hydrophobic property remains intact, as these water droplets beads with very high contact angle on the surface. And then we use this membrane for separating the oil and water mixture. As we have made this prototype, when we pour the water and oil mixture through this prototype, we can see only the oil phase passes through the membrane while the water remains on top of the membrane. That is because the super hydrophobic surfaces are also super oleophilic in nature, which means they are oil loving in nature. So it repels the water, but it can easily allow the oil phase to pass. So in this way we can separate the oil and water mixture using the super hydrophobic membrane. We have also demonstrated that we can design the super hydrophobic cotton, where we have coated this medical relevant cotton to make it super hydrophobic in nature for dressing purposes and other applications. But here you can see that both the surface as well as when we tear this cotton in different pieces, all the different pieces are super hydrophobic in nature, but they are also oil loving, as oil can easily pass through the cotton. And that cotton was used for absorbing the oil from oil water mixture, where we can see the super hydrophobic cotton selectively absorbs the oil from the oil water mixture, whereas when we see the untreated cotton, it only absorbs the oil water which comes in contact with the cotton first. So it remains selective for separating the oil from oil water mixture. The super hydrophobic cotton in that case could be useful for removing the oil from the oil water mixture. However, if we see in broader context, one of the inherent limitation of super hydrophobic surfaces is that they trap air, because of which this property exists. That trap air easily damages in presence of extreme conditions like either the higher or low temperature as well as the higher pressure conditions. The super hydrophobic property compromises its water repellent property. So in order to counter those limitations, another material which is also inspired from the nature, which we call as slippery liquid infused porous surfaces or slippery surfaces. So these surfaces are inspired from Nepenthes pitcher plant. So here we can see this Nepenthes pitcher plant. When the insects walk on the edges of this pitcher plant, because of the slippery interface, those insects fall into the epitome of this pitcher plant because of the slippery layer. So then it was demonstrated that because of this lubricant layer on this surface of the pitcher plant, it remains highly slippery in nature. So with that idea, researchers have designed the slippery surfaces by creating the porous are textured solid and infused with the lubricant, and when that lubricant was tested with the water droplet easily slips away from the surface. So the criteria to design this slippery surface is first is to need a porous or textured surface, and then the lubricant is needed. That lubricant needs to be uh, immiscible with the testing liquid. For example, if we are using the lubricant or lubricant as an oil, it should be immiscible with the water or any other testing liquid. So then the testing liquid, when falls on the surface, it can easily slip away from the surface. So in that way, we can design the slippery surfaces in the artificial means. So these slippery surfaces are having a different or wide variety of applications like anti-fouling, anti-icing, anti-frosting, as well as they can be used for anti-corrosion applications. So as I mentioned previously, that the super hydrophobic surfaces are unstable at extremes of conditions like temperature and pressure. They are only repellent to liquids which are water, with a very high surface tension liquids like water. They are unable to repel the low surface tension liquids like oil and other low surface tension liquids, as well as they are not resistant to various damages and abrasions. However, these slippery surfaces encounters all those different limitations of super hydrophobic surfaces because they are stable at extremes of temperature. They can repel other liquids in addition to water as well. They are also damage repellent. They are also damage tolerant, as well as self-healing property they exhibit. So therefore, but most of the slippery surfaces, they are static in nature. They don't have any dynamic property because they use lubricants which doesn't have any stimuli responsive properties. So these surfaces are unable to show any stimuli responsive behavior. Our idea here is to design the super slippery surfaces which are stimuli responsive slippery surfaces. In our research work, what we have done, we have designed the stimuli responsive slippery surfaces for liquid droplet manipulation. In this project, what we have done, we have taken liquid crystal. As we all know that liquid crystal is a phase which exists between liquid and the solids, and this liquid crystal has some properties of liquids and some properties of solids. One of the best property of this liquid crystals is that they have different properties at different temperatures. So the particular liquid crystal which we take here is 8Cb liquid crystal, and this liquid crystal exists as a solid at room temperature, but we go above room temperature, it acts as a liquid. So with that property, we take that liquid crystal and infuse this into a porous texture. When we infuse this liquid crystal into a porous texture, what we found that this at the room temperature, this slippery surface is not slippery in property. So it shows a sticky. When we put the water droplet at the room temperature, the water droplet sticks even if you tilt the surface to 90 degree. However, when we increase the temperature above room temperature, the solid lubricant becomes liquid and eventually provides a smooth interface of liquid water interface, and the water droplet can easily slide away from the surface. As we can see from this schematic, at So room temperature it spins, but at high temperature it can easily slide away from the surface. And that we can also measure the adhesion force between the surface and the droplet at room temperature and at high temperature. So at room temperature the adhesion force is very high, as we can see here from this curve, from the black curve. But at the high temperature, above room temperature, which we call as pneumatic phase, the adhesion force is very low, which shows that the adhesion between the water droplet and the liquid and the slippery surface is dependent on the temperature. At room temperature it's highly adhesive, at higher temperature it acts as a slippery surface. So in that way we have designed a slippery surface which is stimuli responsive in nature. As we can see here, when we infuse this porous texture with the silicone oil, which is not slippery, stimuli responsive oil, we can see that the silicone oil behaves same in all the temperatures irrespective of the temperature. But in case of liquid crystalline infused surfaces, at lower temperature it is the sliding angle of the water droplet is very high, whereas at the high temperature the sliding angle of the water droplet is as similar to that of the silicone oil. In addition to that, we can also make the surface as a UV responsive slippery surface, where we can infuse some UV responsive materials or ingredients to make it UV responsive, as we have demonstrated here that in presence of UV the liquid droplet can move, while when we turn off the UV the liquid droplet doesn't move. So the displacement of the liquid droplet from one place to another place is based on the stimulus, which is the UV. And we can also demonstrate the trajectory of different liquid droplets based on the UV exposure. So in that way we can design the slippery surfaces which are stimuli responsive in nature, where we can manipulate the droplet trajectory, or we can manipulate the droplet motion based on the stimulus, which could be useful for different variety of applications. And one of the application here we have shown is underwater bubble manipulation. As we know that underwater bubble can be used in various different applications, like energy production, like gas to gas movement, and we can like in the electrocatalysis, all those kind of the different applications. This underwater gas manipulation is highly essential. So here we have demonstrated that this particular surface could be used also for the selective transfer of gas bubble from one place to another using the external stimuli as a temperature. So here you can see at low temperature that the sliding angle for the bubble is very high, while as at the high temperature the sliding angle of the bubble is very low. So with the changing the temperature we can transport the bubble from one place to another, the gas bubble from one place to another based on the different temperature. And here we can see the sliding angle of the gas bubble at different temperatures in comparison to silicone oil, which remains constant all throughout the different temperature. And also based on the bubble volume we can also change the sliding angle. That is because of the buoyancy force. When we increase the volume of the bubble, the buoyancy force acts on that bubble increases as well. That we can see from this schematic. When the volume of the bubble increases, the buoyancy force also increases, which eventually slides at very low sliding angle. In addition to that temperature, we can also use different other stimulus like UV. As I already mentioned previously, UV can be also used for displacing the gas bubble from one place to another underwater, as well as we can also use the chemical which is in the chemical environment, because this liquid crystal is also sensitive to some chemical environment. So if we expose it to different in different chemical environments where it changes its liquid crystal phase, it can also use that as a stimuli for traveling or for movement of gas bubble from one place to another place. So here we have performed some demonstrations where we can use this gas bubble for lifting of some elements underwater, and also use for uh, folding an origami box, where when we put the gas bubbles on different corners or different edges of a box which is unfolded, and when this, because of this buoyancy force, these gas bubbles can fold this simulated box under water. So these are some of the demonstration, and also we can use it for traveling the gas bubbles on different curved surfaces as well. And also we can see like sensing of chemical components, volatile organic components, using this method, where the this volatile organic compounds, they are sensed by the liquid crystal, and they can change the phase of the liquid crystal, and that could be also used for sensing the volatile organic compounds using this method. In addition to the slippery liquid surfaces, as I mentioned, that super hydrophobic surfaces, they are not repellent to different organic liquids. However, the slippery surfaces can overcome some of the limitations of the super hydrophobic surfaces, but also these slippery surfaces, they are also, we can say, they are dependent on the lubricant which is infused in the surface. If we are infusing any hydrocarbon lubricant, which won't be able to repel the organic liquids like organic solvents and all those things. So in order to repel the different variety of liquids, another concept is in the literature, which we call as super omniphobic. The super omniphobic surfaces are those surfaces which can repel both water as well as the oils. So these surfaces can repel all virtual liquids, whether it is an organic liquid, whether it is an aqueous liquid. So in this project, we have designed a super omniphobic surfaces, but most of the super omniphobic surfaces, they are unifunctional in nature, means they can only demonstrate the oil repellent or water repellent or the liquid repellent property. If you incorporate any other functionality into that, it may compromise the another liquid repellent property. So because both the properties are surface sensitive properties, so here in this project we have designed a multifunctional super omniphobic surface. So what we did here, we have designed a super omniphobic surface which is photochromic, means which changes color in presence of the light, but at the same time it is also repellent to water and other organic liquids. So in order to design that kind of surface, we have used an organic molecule which is spiropyrene. Spiropyrene changes its color in presence of the UV light because of the extended conjugated biconjugation, which shifts its wavelength towards the visible region, from UV to visible region. And then we have used FDTS, which is a low surface energy molecule, fluorinated molecule, which provides the oil repellent property, and all of them are combined in a polymer structure and sprayed on a surface. And when we sprayed it on the surface, here we have taken a glass as a substrate, and you can see both the water as well as the oil can be repelled using this surface. Interestingly, this surface can still repel the oil and water, but when we expose it to the UV light, it can change its color from colorless to violet color in presence of the UV light. So therefore, in this project, we have designed a multifunctional super omniphobic surface which repels both oil and water, as well as changes its color in presence of the UV light or the extra or the other light. And we have seen that, and then we have extended this approach to the more realistic application, like we have coated this material on the fabric, and when we coated on the fabric, it shows the similar behavior in presence of UV, and in absence of UV, both the liquid repellent property and the color change was observed. Now the question is, why this oil repellent or the liquid repellent property is essential for these color morphing materials? It has been demonstrated in the literature, as well as it has been shown that these color morphing materials, they compromise their color changing ability in presence of harsh environments. And we have also demonstrated here, when we have two different surfaces, one is super omniphobic and another is only color morphing. When we expose these materials to a concentrated sulfuric acid, we can see here the surface which is super omniphobic retains its color morphing property, while as the surface which is not super omniphobic compromise its color morphing property after exposure to concentrated sulfuric acid, which means that this liquid repellent super omniphobic property prevents the color morphing ability of the material. So it prevents the damage of these color morphing molecules. So for that reason, this super omniphobic property is highly relevant to these color morphing materials. And in addition to that, we have also designed a stretchable super omniphobic surfaces, and in this case we have used a different method, which is a more different method, which is laser engraving. So in this method, what we have done, we have taken a silicon polymer, which is EcoFlex polymer, which is stretchable itself in nature, and then we designed a texture on that using a laser, carbon dioxide laser. And after carbon dioxide laser, we have exposed it to the fluorinated alkyl silane. As I mentioned, this fluorinated silane or fluorinated chemicals are used for designing the super omniphobic surfaces. There is not any method yet which uses any other hydrocarbon materials for designing the super omniphobic surfaces. So we expose this to fluorinated silane to design the water and oil repellent surfaces. As we can see on these surfaces, when we put water and other different oils, all of these liquids can be repelled. Even these liquids can be repelled when we stretch the substrate up to 600% from its initial position. So in all those cases, it retains its super omniphobic property. So which means that the super omniphobic property retains even after stretching to 600%, which can be useful for wearable electronics in the future purpose. And in all these different elongations, the contact angle, which is a measure of liquid repellency, remains above 150 degree, which is a benchmark, and below 10 degree, which is also a benchmark of characterizing the super omniphobic property. In another project, we have designed the super omniphobic surfaces which have some sort of actuation. So the activated super omniphobic surfaces we have designed. As I am mentioning these projects because the sensitivity of these projects is very high, because all of these properties, they are surface properties. So in order to attain the two surface properties or multi-surface properties in a single material is highly challenging. So here we have used liquid crystal elastomer. As I mentioned previously, liquid crystals have some specific properties. They have the different properties at different temperature. So here we are using liquid crystal elastomer, which is made up of the liquid crystal, but they have the elastic property as well. So here we use liquid crystal elastomer as our substrate, which enables the reverse metamorphosis, that is the shape transformation in response to external stimuli. So here we are using our external stimuli mainly as temperature. This reversible metamorphosis makes them ideal for many applications like robotics, artificial muscles, responsive coatings, actuators, and so on. So here in this project, we take liquid crystal elastomer as an example. So how we first design the liquid crystal elastomer. So in order to design the liquid crystal elastomer, you need a liquid crystal monomer, a cross-linker, as well as a catalyst, and then we mix them together in an appropriate solvent, and there is a method of application for the liquid crystal elastomer, which is a very well known and well designed method. And then we design the monodomain liquid crystal elastomer, and then in the next step, this monodomain liquid crystal elastomer was uh, engraved with the laser. As in the previous project, I mentioned that laser engraving was used to design the texture. Here in the similar method, we use carbon dioxide laser to design the texture, and similarly we expose using chemical vapor deposition of fluorinated alkyl silane to make it super omniphobic. The interesting thing about liquid crystals is that it can change its shape with respect to the temperature, that I will be demonstrating in the upcoming slides. So here we can see when we make the super omniphobic with the LC, it shows the super omniphobic property, where we can see the contact angle is above 150 degree and the sliding angle is less than 10 degree for the range of surface tension liquids, as an example here in this inset we can see. And we also demonstrate the bouncing of the water droplet and hexadecane droplet, which are the two extremes of surface tension. Like water has a surface tension of around 72 millinewton, and this hexadecane has surface tension of around 27 millinewton. So this range there of surface tensions can be repelled with this super omniphobic surfaces. And then we have demonstrated the mixing of two individual droplets without any hand exposure, without any hand touching, so only based on the external stimuli. Like we can see at room temperature, it's go in nature, and when you increase the temperature to above its temperature, which is around 80 degrees centigrade, it becomes flat. And when we start decreasing the temperature, the surface, because this is a shape memory material, it can recover its original shape, and when it recovers its original shape, the two liquid droplets can easily merge together, and we can do the mixing of the liquid droplets without using external hand, which are without using the hands involved in the experiment. So, and also in addition to water, other different liquids can be also merged together for microfluidic applications. In addition to these projects, we are also our current project, which is to design the fluorine-free, environment-friendly super omniphobic surfaces. As I mentioned in the previous projects, the main challenge is to design a super omniphobic surface is to have the fluorinated hydrocarbons. So but these fluorinated carbons, they are environmentally unfriendly. In order to, so now our aim is to design the super omniphobic surfaces without using the fluorinated carbons. So in this one we are working on this project, where this project could have a wide variety of applications for designing the environmental friendly super omniphobic surfaces without using the fluorinated chemicals or fluorinated materials, which is currently, or which is widely used for designing the super omniphobic surfaces. Our next ongoing project is designing hydrophilic slippery surfaces for anti-thrombotic biomedical application. As I mentioned in my slippery surface project, so that is the hydrophobic slippery surfaces, means when the contact angle is very high, like above 90 degree, that we call as hydrophobic, and when the droplet slips away from the surface, called as slippery surface, and those surfaces are hydrophobic slippery in nature. So in this project, we aim to design hydrophilic slippery surface for anti-thrombotic biomedical application. So basically, this is like a counter-intuitive surfaces. Generally, hydrophilic surfaces are water-loving surfaces, so they are not able to relieve the water present on the surface, so the water droplet is hard to slide on the surface. So here we are going to design a strategy, which in that strategy we will be designing hydrophilic surfaces for anti-thrombotic biomedical application, and those coatings, if successful, could be used for biomedical devices to make the biomedical coatings on biomedical devices which are anti-thrombotic in nature. In another ongoing project, we are going to design the slippery surfaces for anti-icing and anti-corrosion applications. As I mentioned earlier, that this slippery surfaces have anti-corrosion and anti-icing applications as well. So we are going to design various slippery surfaces which are having anti-corrosion and anti-icing applications, and we will be designing a setup for these kind of the applications in the future works. And if the time permits, in our next presentation or next submission, we'll be talking more about the another projects or another ongoing projects which are some of them may be near to completion. We will be presenting those projects in our upcoming submission. And finally, I would like to thank you again for for providing me the opportunity for this presentation. I am highly thankful to NIT Srinagar and ANRF for providing me this platform to present my research work. Thank you so much. Thank you.